So if you go to OpenStax and go to the tab of contents, and you're going to scroll all the way to the appendices. For the rest of the semester, we are going to be using different appendices. We could not use an appendix for all of our constants for those reactions because those are chemical reactions. These are known things that are easy to measure, like they're consistent. And so the ones that we are going to be using for the rest of the semester, ionization of weak acids and bases, that's next week. So there is actually K values for weak acids and weak bases. If it is strong, it's one way, not equilibrium. So these are equilibrium constants for the acid behavior of things and the base behavior. The base chart is like one of the worst weak base charts I've ever seen because there's only 5 substances in it. It's online. Put more on there. Anyway, solubility. Okay, solubility products. And then the very last thing we're going to be doing is electrochemistry. There, L. Oh, there's half. We don't need half, but L. Half-lives would go with our first order stuff from our kinetics. You do the half-life, then you can plug it into the half-life equation. Okay, so we're going to do J, solubility products. So the way that they have their tables for all of these, once you scroll past the opening of the table, you don't see the headings anymore. So you kind of have to like look at the heading before you start scrolling. And so the value that you see all the way on the right-hand side of your screen is the KSP at 25 degrees, because equilibrium constants are always temperature-based. And so this is a starting point. So if you have your water at 25 degrees, this would be the constant when you multiply all of the concentrations together using the equilibrium expression. Okay, so these are only ionic compounds. If you scroll through, you'll see a bunch of metals. So they are characterized and organized by the metal, and there aren't that many choices, and they are also all the things that we said were insoluble. So back in aqueous reaction times, we said barium carbonate is not soluble and barium fluoride is not soluble. They're teeny amount of solubility. So there has to be a cutoff point. And so the cutoff point is if less than 1 gram of the substance can dissolve in 100 milliliters of water or 100 milliliters of solvent. That is the cutoff point. So if something will not at least dissolve 1 gram, it's considered insoluble. But there are variations of less than 1 gram. Okay. So -32, the equilibrium constant, -32 compared to barium fluoride, -5. Aluminum hydroxide is a lot less soluble in water. This is not the solubility, this is the constant, but it is directly related to the solubility. So the constant, the way you find it is you look for your substance, and all our examples will be in this table, or if it's not, I will give you the number. So all of the choices that I chose for these examples, you would look for the constant in the table if you do these calculations, because they're ones that are in the table. So for our example is barium fluoride. So our KSP is 2.4 times 10 to the -5. So we need that constant. So we are going to do the calculation. And so everything we have been leading up to is we're talking about a supersaturated solution. And what we can do with the information about a supersaturated solution is figure out the molar solubility. So over here on the previous page where I put X is your unknown amount. When we're talking about equilibrium, this is a specific situation here. X for this situation is the molar solubility. So this is a very, very, very narrow focus. So we don't go back to the previous problems and say, oh, X is molar solubility, because they weren't solubility, they were reactions. So this is when we set up a table of a supersaturated compound. And we use minus X for the amount of the solid that dissolved. The maximum amount of solid that dissolves and still has solid left will be the solubility. Okay. So at equilibrium, we have X amount of barium ions and 2X fluoride. So if we go back to our first page and we write our KSP expression, which was KSP equals barium ions to the first times fluoride concentration squared over 1. So page 1, we did the dissociation and expression. Page 2, we set up the Rice chart. And so to finish off getting ready to do the calculation, you plug in equilibrium data into the expression. And so where did we just find KSP? That was in Appendix J. What was our value of KSP in Appendix J? 2.4 times 10 to the negative 5. Okay, we used a Rice chart to determine equilibrium barium. And what is our equilibrium barium amount from our Rice chart? It is, barium is X. And that is raised to the first power. How much fluoride is there? 2X. And that is raised to the second. So this is the way that you need to write it. So inside the parentheses is X raised to the first times inside these parentheses is 2X squared. When you do one of these problems, your coefficient will always match your order. Because how do we use the coefficient in a chart? As the X factor. How do we use the coefficient in an expression? As our order. If these don't match, then you have left something off. Okay, then we are now in the do the math step. But you need to do the math correctly. So I'm going to do it step by step. And as I recommend that you do it step by step so that you don't jump and do this wrong. We will not need the quadratic equation for any of these problems. Because all of our X's are going to be combined into one factor. And so we can isolate the variable and isolate the number on the other side. Now, there is all the math. It is 2X quantity squared. So you have to square the 2 and square the X. Then you multiply the X squared by the X to get X cubed. And so you end up with 4X cubed. And the K is still sitting on the other side. Wait. So when you rewrite, don't forget to write the constant over to the left. So as I mentioned last week, even if it's simpler math, when you rewrite it, rewrite all the parts. Don't think that you're going to go back to a previous step and pull the number back. Okay. So I simplified this, and now I need to isolate the variables. I need to get rid of the 4. So I got to divide both sides by 4. And then that'll give me x cubed is equal to 6 times 10 to the negative 6. And then I did a cube root. So whichever calculator you have, you're going to need to review how to do cubed and fourth and fifth roots. There are easy ways and there are difficult ways using your calculators. Somebody like found the actual mode and it was hidden deep within the calculator. So it took like 5 or 6 different buttons. I'm going to use the $10 calculator here. And now there's a button for it. Okay, so I'm going to do 6EE negative 6. And then I'm going to do the cubed root. And so it's for me, it's my shift. And then this. And then I got to do it to the cube root. So this should be your x. So your answer would be 1.8 times 10 to the negative 2 or 0.018. I'm rounding it to 2 digits because the only number is the K. And so there's only 2 digits there. So I rounded it to 2 digits. Okay. X is the molar solubility. So molar solubility problems, when you solve for X, that actually is the answer. But we have to put it into molarity because it's molar. And so what is the abbreviation for molarity? Capital M. And so when you get your X, you're going to stick a capital M on it. And it is the molarity of barium fluoride. So then you just tack on the compounds formula. So this is the finishing step. This is the finishing touches on the answer. So you plug in your X amounts, and then you do the math. And with this math, you will be able to isolate the X value on one side and the number on the other. And then you do the smallest is going to be square root. And then you'll have a cubed root, a fourth root, a fifth root. That's about it. When you get your X, you'll round it usually just based on how many significant figures was in your K. And then you stick the unit on it, which will be molarity because it's the molar solubility, and then the formula. So it is this X right here. That's because we want to know how much of that compound dissolves, which is X. Okay. This example right here, this is all of the steps written in one. So page 1, page 2, page 3. So this is page 1, which is write out the dissociation. And it's going to be equilibrium because it's solubility. And then you would set up the chart just like on page 2, where you put solid. Okay. And you have your expression, and you're going to plug in your X quantities into your expression. And where will you find the KSP for this? In Appendix J, because I chose ones that are in Appendix J. If you don't know the formula, you can figure it out, or you'll find it in Appendix J. But there is iron 2 and iron 3 hydroxide. So you got to be sure that you choose the iron 2 for this example. Iron 3 is in the homework. Okay. And then you'll just solve for X. And once you get X, you will do molarity of iron 2 hydroxide. Okay. I'm going to scan these examples into Moodle, but this part here is not on the test. Doing a rice chart is on the test. So if you can see how we used it the same way as before with X's, our biggest difference is the products were not part of the expression because they're solid. It's the only difference. The math is still the same.